All right, today we're talking about gravity. This is not a discussion about weight as we've had in the past. So what we're not talking about, not talking about the force of gravity being mg. In fact, we're going to prove today that the force of gravity is mg. So the whole point of today's discussion is to understand the concept of gravity. And it's not on its surface a particularly difficult concept, but it has interesting implications in the way in which we apply it to other situations. So let's start with kind of a simple system of two planets. The force of gravity is a force of attraction between the two planets. The force has to be the same size on each. That's, of course, obeying Newton's third law. But there's other properties of gravity that are interesting, I guess. According to the rule, Newton's law of universal gravitation, the force of gravity between any two objects is the product of the two masses divided by the separation distance squared times a constant. So let's handle that real quick. We need the mass of each object, m1 and m2. The separation distance refers to the separation distance between their centers. We'll call that r. And g is something called the universal gravitational constant. Notice it's capital G. That's incredibly important. We're not talking about lowercase g. That's the acceleration of gravity, not even a little bit. This is something that we believe is the same everywhere in the universe and has been measured countless times. In fact, we rely on it to be the same everywhere in the universe. That's how we base our movements in space, knowing that we can count on gravity to always act and behave the same way around any other object, not just the Earth. The value is 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. And although it's on it's on your equation sheet, keep the value in mind. It's really small, and because you can probably imagine, we're going to have lots of numbers that are probably pretty big if we're dealing with planets and orbits. This value ends up kind of keeping the number within an appropriate range. It makes the units work out correctly. But one of the biggest problems with doing these problems isn't that this is particularly hard. What makes this hard is you're going to use a lot of big numbers, and you're going to want to shove them all into your calculator, and that's where you're going to come into making mistakes. So I'm going to tell you from the beginning, your best bet here is to make sure you use the EE button when dealing with the numbers here. So you're using scientific notation appropriately. And the next thing is, don't do too many steps in your calculator. Because I'm not there and I'm having to do this from remote, I'm going to probably stop each step and make sure you're doing your mathematics correctly. So let's start with some basics. And I'm leaving out stuff here. I'm purposely leaving out some things. I just want to start with a few basics. In fact, a simple basic is, let's deal with the weight of a human and figure out where it comes from. To do that, I'm going to talk about maybe the force of gravity between you and the Earth. So let's get a new fresh page here. Let's say that I drop you near the surface of the Earth. Center of the Earth is over here someplace. You are there. You apply a force of gravity to the Earth in this direction, and the Earth applies a force of gravity to you in that direction. based on Newton's law of universal gravitation, there will be the mass of the Earth, the mass of you, and then there's the separation distance squared, all times g. For argument's sake, let's say in this example, you use your own mass, I'm going to use my mass, and we'll use the accepted value for the mass of the Earth and the accepted value for the radius of the Earth to make this calculation. What we're going to do is we're going to find the force of gravity on you. So I'll give you a few pieces of information, although I should make you look them up. The mass of the Earth. The mass of the Earth is 5.97 times 10 to the 24th kilograms. For today's lesson and for all lessons this week that use large numbers, I'm going to use the just a capital small e here to indicate times 10 to this whatever. That's to clue you in that I'm expecting you to use the EE button on your calculator. All right, radius of the Earth. Now, I know that I said we're going to drop this guy above the Earth, but the Earth is really big, so that essentially means we're at the radius. So the radius of the Earth is 6.37 e to the 6th meters. All right, so we're going to find the force of gravity on each of us. I'm going to use my own mass, and my mass is like a lot. I mean, it's so much. So I'm going to use my mass, which is 100 kilograms. You use whatever works for you guys. So it's 2.2 kilograms. I'm sorry, 2.2 pounds per kilograms. So if you take your own weight in pounds and divide by 2.2, that'll give you your number of kilograms. All right, here we go. Force of gravity. There's a lot of pieces, so let's put them all together. Mass of the Earth, 5.97 e to the 24th. Mass of me, just a little 100, all divided by radius of the Earth, 6.37 e to the 6th squared times 6.67 e to the negative 11th. All right, so you can put all this in your calculator and just have it knock out what you need, but you're doing this for the first time, and some of you are just not great calculator people. What's hilarious, if I was in class and we're all doing this together, I'd get dozens and dozens of different things. So I'm going to do mine in steps, and I'm just going to multiply all the top numbers together first. So 5.97 e to the 24th times my 100 times 6.67 e to the negative 11th. And I get, for the top, 3.98 e to the 16th. Now on the bottom, that's 6.37. I gotta square it, so it's gonna be huge. And I get 4.06 e to the 13th. Now, yeah, I know you don't have to take these two steps, but trust me, putting it all in your calculator is just never helpful. I get 981 newtons. Now, this shouldn't be a surprise. You should have your own number here. And whatever your number is, I want you to think, if you were actually dropped above the surface of the Earth, so you're not touching the Earth, but you're close to it, then by Newton's second law, the net force on you would equal ma. Well, we just found that unbalanced force is, well, a different number for all of us, but for me, it's 981 newtons, and my mass is 100 kilograms. So right here, I could prove that my acceleration ends up being 9.8 meters per second squared. Now, whatever number you guys have used for your mass, you should still get 9.8 meters per second squared for the acceleration, because our force of gravity equation should agree with our measurements near the surface of the Earth, and it does. In fact, that is one way to measure the gravitational constant. is to have a known acceleration of gravity and use it to work backwards to get the acceleration constant. Now, it's not actually how it's done, but for a simple laboratory experiment, we could do it that way. Now, for just a minute, I want to back this up. We've used this relationship for a simple calculation. I want to talk about one more thing, something that I think is obvious here. It's what I just did as our experiment. If you wanted to find the acceleration of gravity on another planet, and this is not an uncommon AP question, so let's just, every time I come up with something I think is a good AP question, I'm just going to stop and say, and put a number next to it and say, here, question number one, find G. Can't write today. Find G on other planets. Well, let's see what you would need to have to find G on other planets. Well, one way is if you're using this, it looks like to find G on other planets, you assume that the net force on an object near that planet is equal to ma, where this is just some object. So no longer are we flinging U, we'll say that we are just flinging some object near a planet. Well, if the only force acting on that is the object, then the mass of the planet times the mass of the object all over r squared times g equals the mass of the object times a. Clearly, the reason why we all got the same answer for the acceleration of gravity is because we multiplied by our mass, and then we immediately divided by our mass, so the acceleration of gravity on another planet can be found using this relationship as well. This is probably something you should know and keep available to you. This is how they find it on other planets. This is how you find it on other things. You can do it experimentally, but this would be a theoretical way. Also, this is a way for us to figure out the mass or radius of other planets. Now, the radius for other planets can usually be determined visually. If we can see the planet, there's ways for us to use geometry to measure the radius of another planet. Mass of another planet is harder to do. We tend to do it by looking at orbits of things around that planet or the way things behave around that planet. We basically are looking at how things accelerate near that other planet. Okay. That's just the start. There's much more to this relationship that we have to talk about, and I've left a few things out. So in order to get you guys a little bit of practice, what I would like you to do is to take one moment and figure out what is the acceleration of gravity on the moon. So let's say we have an object that's going to be dropped near the surface of the moon. We want to know what its acceleration is. I want you to find the acceleration of gravity near the surface of the moon. I could help you out. I mean, I know you have access to the internet, but if you're actually doing what I'm asking you to do and you're watching my little videos, then I could probably be convinced to give you the information you need. But let's see, do you know what information you need? Just raise your hand. Oh, some of you probably did. Haha. Mass of the moon. You're gonna need that, 7.35. That's not a great 7.35, either 22 kilograms. What's funny is, compare that to the mass of the Earth, and it's really hard to have any idea whether these numbers are close or not. I mean, some people see this and think, well, the mass of the moon is bigger because it starts with a 7. Most of you guys are smart enough to realize, no, that's not true because there's orders of magnitude different. Usually to compare two numbers, one of the things you do is you put them in the same scientific notation. So I'm going to slide this over 2 places, and that puts it in the same scientific notation. So e to the 22 here, e to the 22 here. So now when I compare the numbers, I'm really only comparing the front part of the numbers. That lets me make a comparison of the relative size of the two numbers. It may not appear like it, 597 compared to 7 doesn't seem like it's very much the same, but our moon is huge compared to the size of the planet. There's no other planet except for Pluto whose moon is so big compared to the planet, and we demoted Pluto because it's kind of a weird thing out there. Every other planet, its moons are either uh, like asteroid captures. That's what Mars has, two asteroids that are kind of revolving around it. Or in the case of some of the gas giants, they have they have moons the size of planets and dozens of asteroid captures as well. So our moon is actually very big compared to the planet, and it has been a stabilizing force in our planet. And no, the movie Moonfall is not true. There's not. I'm not going to watch it. It looks horrible. But if you watch it, give me a solid review, because I just don't think I can stomach it. All right, so back to work. You'll need the radius of the moon, which I'm sure we know to great. I'm sure we know to great accuracy, and it's quite big, 1.74 e to the sixth meters. So again, compared to the Earth, it's got a huge radius. Obviously, if you look at those two, it's got a big radius. Volume. If you're I don't know, a curious person, you should compare the two densities. Uh, you might find that interesting. Probably not. I would find that interesting. All right, that's all you need. So I'm going to stop here. You should hit the pause button and take a moment and find out what the acceleration of gravity on the surface of the moon is. So don't come back for a few seconds. Just take a moment and work this out. Now, if you did your work correctly, you find that the acceleration of gravity on the moon is about 1.6 meters per second squared, or about 1/6 or 1/7 the acceleration on the Earth. Now, to make sure you did it right, and I hate to always go over stuff, I'm going to go over it. If you got that, skip this part. It's going to take me about a minute and a half. If you didn't get that, well, let's pay a little attention here. The net force on our object equals ma. We're going to say that gravity is the only thing pulling our object down. So that would be the mass of the planet times the mass of you, or our object, times g over r squared has to equal the mass of you times the gravity on the moon. Remember, this is the thing that we're talking about. Even though the force on the moon is the same as the force on you, we're focused on the force on you, not the force on the moon. We're talking about what you're doing, what your acceleration is, not the acceleration of the moon. If we put the moon's acceleration in here, we'll find out it doesn't accelerate very much. Although you and the moon both experience the same force, it's far more effective at accelerating you than it is at accelerating the moon. So if we want to figure out the acceleration of gravity on the moon, obviously the mass of you cancels out here. We're left with the mass of the planet, or in this case the moon, 7.35 e to the 22, times g, 6.67 e to the negative 11th, divided by the separation distance. I'm going to keep saying separation distance instead of radius, and I hope you'll understand why, but it's not always going to be a radius. So that's a 1.74 e to the sixth squared, and this equals the acceleration of gravity on the moon. Again, yeah, I think you can plug all that into your calculator, and most of you will be successful, and you'll get the right answer. But as we found in the past, and as I continue to find even now, sometimes if you're having trouble, break it up into small pieces and do just one portion at a time. Especially if you're not doing your scientific notation correctly. Use that EE button to do scientific notation. I get 4.9 e to the 12th in the numerator, and when I square that 1.74 e to the 6th, I get 3.028 e to the 12th in the denominator. Of course, you divide those two numbers and you get your 1.6 meters per second squared. All right. So far, this stuff has been kind of kid glove kind of stuff. Simple, straightforward. I would teach this in an honors physics class. This is not the level that I need you guys to be working at. I just wanted to introduce the formula. Now, the AP exam uses this relationship many different ways. But to be honest, a lot of what they tend to do using a relationship like this are ratio questions. And you guys have become more familiar with ratio questions, but understand that ratio questions are intended to see if you understand the nature of the formula, and it's less about the actual phenomenon. So here's a simple ratio question. They'll say there's two planets. There's the Earth, and then there's, planet X. They'll say something like, planet X has 3 times the mass of the Earth and 2 times the radius. What's the acceleration on planet X? Again, they'll say that planet X has 3 times the mass of the Earth, and 2 times the radius, 2 times the radius of the Earth. And they'll say, what is the acceleration of gravity on planet X? Now notice, they don't give you the mass, they don't give you the radius. And you might think because you can look up the mass and the radius, that's what you should do. But usually you're not given that on the equation sheet unless it's for a specific problem. So they have an expectation of a different process. They know that you should be aware that the acceleration of gravity on the Earth is 9.8 or 10. What they're asking you to do is to deal with a ratio problem. Now, there's a variety of ways to do this problem. I'm going to show you one. First, to do this problem effectively, I think you need to know how to calculate the acceleration of gravity on the Earth using a formula. That should be clear that that's what this problem is steering you towards. So I think we know this is the formula. And again, I'm going to call these ratio problems. So we know that if I want to find the acceleration of gravity, I sub in for net force and get mass of object times g on this planet is going to equal mass of planet times mass of object times g all over r squared. Now, we know what this value is on the Earth. We know when we cancel this out, and we write g for the Earth, that'll equal mass on the Earth, g over radius of the Earth squared. And we know that equals 9.8. So if I want to find the acceleration of gravity on planet X, then I'm going to say, okay, the gravity on planet X has to be the mass of planet X times the radius of planet X squared. Now, I don't know the mass of planet X or the radius. I do know that it's 3 times the mass of the Earth times g all over 2 times the radius of the Earth squared. Now, you've seen me do this before. You know kind of how I feel about this. Your job here is to put in your substitution and then pull out the number portions. So I'll pull out the 3, square the 2, pull out 4, and what I'm left with is mass of Earth, g over radius of Earth squared, and I should have a clear substitution. I'm trying to collect the variables, and when I collect those variables, it gives me a pathway to calculate without knowing the mass of the Earth or without knowing the mass of this weird planet or any of that stuff. Because I know how to get the acceleration of gravity of the Earth, and I know the acceleration of gravity of the Earth, I can use that to figure out the acceleration of gravity on planet X. So these are ratio problems. They show up in multiple choice. I don't want to spend a lot of time on them. The ratio problems are usually they solve for something like this, but they could also be like this. And this is for you guys. Two objects Object 1 and Object 2 are a distance r apart. This is mass 1, mass 2, and they currently experience a force of attraction of 10 newtons. What force do they experience when they are 3 times further apart? Try it. Again, I'll say, what will be the force they will experience when they are 3 times further apart? I'm going to pause it. Let's see if you can figure it out. All right, so the answer is 1.1 newtons. If you got that, yippee. Move on past this. If you haven't got that, all right, you should watch, because I'm going to try it again. The original force, m1 m2 over g divided by r squared equaled 10 newtons. Our new force, m1 m2 g over 3r squared. So I sub in the value that changed. Now I'm going to factor out the number parts that changed. I have a 3 squared, so that's going to be 1 over 9, and I'm left with m1 m2 g over r squared. This is my original situation, which is 10, so I have 10 lengths as my new force. You got 1.1. Not terrible. Probably the most important part of this conversation is to talk about orbits. Orbits are a special relationship, and there are types of orbits. We're going to talk about a special case of orbits right now. We're going to talk about circular orbits only. And circular orbits, like I said, are a special case of orbits. And I don't think it takes a rocket scientist to tell you why they're special. A circular orbit is one that is a circle. So that seems pretty obvious to me, but let's be really clear. Most orbits are not circular. Most orbits are elliptical, and because of that, they are a little more complicated than what we're going to talk about. For an object to be in circular orbit, the force of gravity causes centripetal acceleration. That's right. So for an orbit, one, it's circular. We're talking about circular orbits. And in there, first thing you need to realize is that gravity causes or provides the centripetal acceleration. There are 2 things you are often required to deal with when it comes to orbits. Thing number 1, the time for an orbit, usually called the period. And the other thing is the velocity of an orbit. And this is the tangential velocity. So we're going to talk about the orbit of the moon around the Earth. That's what I always start with, and the reason why is because we have an idea of how long it takes the moon to go around the Earth, and because we already have that idea, it makes for a good starting point. And to do this, you're going to need to have at the ready two things. Obviously, the force of gravity, so we need Newton's law of universal gravitation, and the centripetal acceleration. Now, here's one of those days where, it won't seem incredibly obvious why I'm saying this, but you need to become familiar with the terminology. This R is not radius, it is separation distance. In tomorrow's discussion, when we talk about more realistic orbits, you'll understand why I'm doing this. Separation distance, this one is radius of curvature. Look, even in orbits, these don't have to be the same number, especially in non-circular orbits. So just hear me out. Make sure you know the difference between those, because what I'm about to teach you today about the Earth and Moon isn't accurate because of those two words. What we're doing is an estimate today. So that's what we're going to start with, the Earth-Moon system. And I've given you lots of information already today about the Earth-Moon system, so you should be able to go back through for any value that you need, except there's one I did not give you. If I want to calculate the period, then there's several steps I should do to get there. And I'm going to do this two different ways. One, I'm going to do it in steps, and then at the end, we're going to put it all together into a single formula. The formula we're going to do at the end is not on the equation sheet and is not worth memorizing because it's too easy to put together and prove on your own. But let's start with the beginning. If the Earth-Moon system has a circular orbit of the Moon around the Earth, then we could say that the net force on the Moon must equal MAC. So circular orbit questions begin just like any circular motion problem, that we believe the unbalanced force causes centripetal acceleration. In the case of the orbit of the Moon around the Earth, we're talking about the mass of the Earth times the mass of the Moon divided by their separation distance squared times g. And that has to equal, so here's the important thing, what m are we talking about here? In the case of this problem, we're talking about the mass of the Moon. It's in orbit about the Earth. And I'm going to immediately sub in v squared over r. And for a circular orbit, this r, the radius of curvature, is the separation distance. Again, be careful. I'm going to flip the script on this tomorrow, so be careful, be prepared. So now, the first step in finding out how long it takes the Moon to go around the Earth is to figure out how fast the Moon is going around the Earth. I hope the first thing you notice is that it really doesn't matter what's in orbit. What matters is where that orbit is. So we can cancel out the mass of the Moon immediately. Next, we can cancel out one of the r's. This only occurs because the radius of curvature and the separation distance are the same. Now what this leaves me with is mass of the Earth times g over r equals v squared. So if I want the velocity of the Moon as it travels around the Earth, there it is. All right, everybody, try it out. You need something, though, don't you? I can handle that. So the Earth-Moon separation distance, and in this case, the radius of curvature, is 384 times 10 to the 6th meters. I say it that way because we have the radius of the Earth in a value that's times 10 to the 6 meters, and the radius of the Moon in a value that's times 10 to the 6 meters. So this gives us a way of comparing the Earth-Moon separation distance to the size of the radii. It's also how I kind of memorized it, but I did look it up just to make sure. So there, you have everything you need now to figure out the velocity of the moon about the Earth. You should pause the video right now and see if you get the right answer. So did you get the right answer? Because I got that the velocity is 1,018 meters per second. Hard to know if that's fast or slow. You guys don't have a good feel for speeds, but that's 3 times the speed of sound in air, or nearly 3 times, yeah, more than 3 times the speed of sound in air. And if you're trying to land on it, it's moving pretty fast relative to the Earth as it goes around the Earth. So I'd say it's moving pretty quick, but we'll see some other stuff later that will maybe prove that wrong. This is the speed, and it's the tangential speed of the moon around the Earth. But like I said, that's only one stop. I'd also like you to find the period of the moon around the Earth, and we're going to try and compare that to the known period. Usually if I'm in class, I try to talk about this, but I don't have that capacity or that luxury. But the period of the Earth around the moon is 28 days. We should see what the period is that we calculate. We're not going to get 28 days because we're making a mistake. This is why I want you to do this. Now, if you don't know what to do next to figure out the period of the Earth, then I'm going to have you come back to this point and think about something very carefully. We know how fast the moon is going, and we know the radius of curvature, which means we could recognize that the velocity of the moon must equal the distance it travels divided by the time it takes to travel it. If we want the time for one circumference, that will be the velocity of the moon about the Earth. We could use it to figure out the period. So we've already made quite the leap to get here. All we have to do now is place that here or place that here and solve for period. I'm going to place it in the bottom one, and my expectation is that you'll be able to solve for the period. Actually, let's make it easier. I need more room anyways. We'll place it in the top one. And our job is to solve for period. So, mass of the Earth, G over R equals 2 pi R over T squared. So now that we've done that, we just want to find T. So I think the best way probably is just to go ahead and square this side. 4 pi R squared over T squared equals MEG over R. And then I'm going to cross multiply and get T squared on its own, which gives us 4 pi R cubed over MEG. And then, of course, take the root of both sides. There we go. All right. Now, again, this is one of those things where you need to just try and bust it out. I know that the AP exam doesn't often use numbers, but I think you should be proficient here and take a moment and see what you get when you try and work all that out. Find out what T is. And you're going to get a value in seconds. And clearly that's not what I'm looking for. So you'll need to convert it to days. I will give you the answer in seconds, but you take a moment and try it. So hit the pause button now, and then come back and see if what I write down is the same as what you got. Oh, and oops, I didn't square the pi. Make sure you square the pi there. That's right. Now we're good. All right, I get like a lot. 2, 3, 6, 9, 3, 3, 4 seconds. So, I mean, that doesn't really have any meaning. I don't know what that is. So you should endeavor to find out how many actual days it is, and you get 27.4 days. That's me dividing by 60 twice and dividing by 24. So, first, it's close to 28 days, but it's not 28 days. So you can just go outside and see that the moon goes around once every 28 days. What's going on here? Yes, we have made 2 mistakes, and those are mistakes we're going to talk about tomorrow, because I think we're probably the limits of what a Monday lesson should be like, probably more than that. So I have posted practice. It's out of your textbook. It goes along with this video. Yes, I'm asking you to do it tonight. I know this is inconvenient. I know you guys will do great anyways, and so I can count on you guys, and I appreciate it. And for all of you who have contacted me, thank you. I will explain what's going on, but it's not going to be today. So have a great day, and I look forward to when we can be together again. Take it easy.